Hello everyone. This video I'm going to show you how to work with scratchANN with another test case study. If you're starting from this video, I suggest you to go to the previous video. First, watch the demo we had, introduction to this scratchANN, and the case study we had for energy efficiency dataset. If you did that, then I guess this should be fine for you to watch this one. So we started in the previous video, just a quick overview. We work with this library to create multi-layer perceptron artificial neural network. It's a library I developed for scratch in C for those people who want to start developing artificial neural network, specifically multi-layer perceptron from scratch. Then let me just if you're familiar with the basics, I think you should be fine to watch this. But anyway, let's just start. If you go here, we have more examples. One of them is breast cancer. You just need to download these two files. This is the data. This is the source code which we keep the inputs to create the model to train on this breast cancer dataset. The rest of the files is exactly the same. You can just follow these bullet points here. This is the code I also use to extract the data and save it into this format. These are the files I have on my local computer, so the rest of the files is exactly the same. If you open this breast cancer, you're gonna see a bunch of inputs, and the only output, last one, which is the target, is a binary target. It's going to it's going to identify if a piece of, I don't know how to say it, I don't know the medical term, but the piece of mold is a dangerous or not dangerous cancer. So the output technically is a binary decision. We have to, let me see, okay, I'm recording. The output is just a yes or no. If we're gonna find out if it's dangerous or not. This is the data set I have, and the number of inputs, we have 30 inputs, one output. In another word, the first layer, these are the inputs, and I'm going to have this is neural number 30, which is going to receive the X last input, and the only output I have, this is the input layer, and this is the output layer I have. Okay, and this one, because it's a binary type, the options we have for binary, well, it depends how you want to program it, but I usually go with just change it. I usually go with sigmoid. If you know how sigmoid function works, sigmoid function, the output is going to be a value between 0 to maximum 1, and then we're going to say, if, let's say, depending on what threshold you want to pick, if the value is bigger than 0.5, then we're going to say, okay, it's class number 1, for example. If the value is less than 0.5, then we're going to say it's the class number 1, or the answer is no, or yes. It depends how you want to label your data. Anyway, I have the data here, the same data, I have it here, and these are the data is written in a way so that, these are all the things we covered in the previous video. I suggest you to watch to start with that one. These data are written in this format, with the tab space between each column, and the lines starting with syntax with this symbol is going to be considered as a comment, are not going to be read, and only these data are going to be saved in a 2D array. It depends. If you want to read the data from Excel file or another format, you just need to change the implementation of this function. This is what we know so far from the data. The output should be a binary. Whatever I have in between is going to be my hidden layer. I might have 1, 2, 3, it depends. After developing the model with a scratchANN, I want to compare the efficiency with what we have on TensorFlow. I want to see how much scratchANN, which is an open source library in C, is efficient compared with the TensorFlow model and multi-layer perceptron model in TensorFlow. Let's start with I want to introduce you to the files we have. The only thing, another thing that you need to change is this make file. Also, this is the demo file. Just download it. So I just need to change this demo file. Instead of referencing to this demo, reference to demo breast castle. And then the file I want to read, already base inputs are set up inside this demo breast cancer. This is the file I want to read the data from. I already have it in the current directory. And then it's a binary output. This is what we know about the data. I want to print the results every epoch. I want to have just 2 epochs. This is the learning RAM batch size. 70% of the data are going to be used for training the model. The number of the neurons in the input layer. This is the number of the inputs in the input layer. Is 30. It depends. It's something that we decide based on the data, and the output has only 1 neuron, which is going to be a binary. And whatever I have in between, it's my decision. I can have, right now I have 1 hidden layer with 64 neurons. I can increase it to have, let's say, another 50 neurons in here as well. So this means I have 64 neurons. Yes, it's 64. And also the whole thing is connected together. So it's just, you should know the basics of neural networks. We covered that in the previous video. Anyway, and then essentially all these things are going to be connected to the output layer, which has 1 neuron. The type is binary, and we want to shuffle the data. We want to standardize the data. Why I want to do that again? For this specific data set I have, you can see the range of different inputs is different, and I want to have more, I want to reduce the instability in data sets. You can see this is, let's say, much smaller than the range of, for example, this one. And if I don't do that, we'll cover this. An input is going to be times a weight, and that weight might be quite large to train for this one, but when it's large to multiply by this value, then it's gonna create NaN in This is the problem that also TensorFlow, it can create an issue in the TensorFlow as well. Unless you have some solutions, you have to standardize data or using another optimization algorithm, but it's always better to standardize the data. Then I want to save the model. I want to, how many threads I want to use. Let's just keep this one. This is for power computation. Let's say if I change it to, every CPU core has 2 threads. So technically I'm going to use 2 threads, one CPU to do the power computation. I'm going to change this one for simpler activity function setup. This means that in here, the first hidden layer or the second layer, this is the second layer, is gonna all all of these ones are going to have value activation function. The last one is going to have a sigmoid. And the number of the configurations I have in each layer, this one has 1 and this one has 1. Again, if you haven't watched the previous one, this, let's say I have let's say I have sigmoid, and this is the proportion of each activation function in each layer. So if I change it to 0.5, this means 33% of the activation functions in this layer are going to be a ReLU, and 67%, let's say, just round up the value, 67% of the activation functions are going to have sigmoid in this activation function. Then if this is the case, I have 2 configs here, then I have to change this one to 2. But let's right now just keep it simple, and let's remove this one. This is the same setup. We're gonna compare the results with what we have on TensorFlow-based. Then I'm going to read the data. Reading the data, file name was given here, so I'm going to read the text file. Then if the shuffle boolean is true, the data is going to be shuffled. Then I'm going to split the data into train and test data. It just, the name is different, works the same way. I called it validation, but actually it's testing. So I split the data into train and test. And 70% of the data, 70% of the samples were used to train the data. Then I deallocate the memory. You can change the implementation. This is not the most optimal, the most efficient way to program this. I just, to keep it everything simple, I did it this way, but you can change it in the future. Then I standardize the inputs because the range of the inputs are quite different. I needed to do that, otherwise my model is going to be unstable to train on the data. I create the model, I get the summary, everything is the same as the previous video. I train the data, I save the model on my local disk with the file name of model, and also the format of the file is text. I'm saving the weights and biases which have been trained into a text file, something I can read in the future and see what are the weights. And in the future, while I free up the memory, in the future I want to retrain the model, or I want to use the model. I don't want to waste my time, hours to train a model, then not being able to save it. So I save the model, then I want to load the model. In the future, let's say, for example, I want to retrain the model with a new setting for 2 more epochs with a new learning rate, or any other setting you want. You can retrain the model. Already was trained, and now I'm going to just train it a little bit more. And then we're going to see the results, and then free up the memory and free up the memory for the data I read from the text file. Let's do a few tests here to see how this scratchANN is going to work. Simply just make and then run the code. This is what I have. So the number of the samples, 569, which is this one. I have 5, every row is 1 sample, and essentially in total I have 569 samples. The number of the features is the summation of all the inputs and also the outputs. So 30 inputs and 1 output. The data is shuffled in here, and then I have I split the data set into train and test, or again, this is just, the name is different. Actually, we're using that not for validation, we're using that for test. 70% of the data is being used for train, 30%, or the rest, actually the rest is used for testing the model. Inputs are standardized here, and then I create the model based on the architecture I had here. I create the model, and after creating the model, I want to see a summary of the model I just created. The number of, let's just go through each layer. The first layer, which is the input layer, had 30 neurons. It doesn't have any trainable parameters. It doesn't have any activation function. Second layer, or in other words, the first hidden layer, has 64 neurons, and the number of the trainable parameters is 9084. Which is the same name as one of my favorite books, George Orwell. Quite interesting. Okay, so maybe I can show it what's happening here. So I have 30 inputs. This means every neuron has 30 weights plus 1 bias. Weights and 1 bias, okay? And then I have I guess 64 neurons here. This means times 64. This is the number of the trainable parameters I have in this layer. We go back. Oh, it's actually here. So this is the number of parameters in this layer. The activation function for this layer is only ReLU. This is the way I configured the activation function. I said all the neurons in this layer is going to have an activation function of ReLU. The next one, or the last layer, or the output layer, has 1 neuron, and this 1 neuron, because the previous layer had 64 outputs, this means this neuron is going to have 64 weights plus 1 bias. And this is the number of trainable parameters. I have only 1 neuron, so this is the number of the trainable parameters in the last neuron I have. The activation function I chose for this neuron is sigmoid. That's why it says the sigmoid activation function in this neuron is 100% sigmoid. Anyway, the total number of the trainable parameters 2049. The batch size 32. The number of epochs 2. This is the learning rate. So as soon as I call this train, is going to start. It's going to show me a bunch of. It's going to show me the setting that I'm going to train, or the model is going to be trained quite soon, because all these inputs are going to be printed inside this train model. And essentially, you have 2 epochs. You can see already the accuracy is quite large. That's why I said only 2 epochs is enough. You need to understand the concepts of overfitting and stuff like that. I'm not going to go through the details. This is the training cost for, you can just go check how the binary cost is on the internet. You can search on that, and the accuracy as well. The accuracy, well, if it's right, if it's correct, class is predicted, or it's wrong. If it's right, then it's going to give, we're going to give it 1 point. If it's not, then we're going to say, okay, that was not actually a successful prediction. In another word, this model is 96% capable of predicting these 0 1s correctly. For 96% for train data set, and 96% almost also for validation, or in other words, train data set. Then I save the memory on the local disk. So technically, this is the model I just saved for each layer and each neuron. So technically, this is the first all this active. For every neuron, I'm going to save all the weights, and then for last one, how many I have? Okay, for the last layer, I have only a sigmoid, which has 64 weights and 1 bias to be saved. This is the way I save the model, because I want to, in the future, load the model again, reuse it, or retrain the model in case if it's necessary. Then I free up the memory. I don't want to have any memory leak. That's why I free up the memory, deallocating the memory. This means at this moment I don't have anything of my trained model anymore. Then I load the model. I just pass the name of file name save, which was this one. To load the model, where was it? Oh, to load the model, and then I want to retrain the model with new settings. I'm changing the learning rate, and I just training the model for 2 more epochs to see if the things are working properly. Then I free up the memory after doing that, and then I deallocate the memory. You can see everything here after I load the model, and then I want to retrain the model for a new setting for 2 more epochs. You can see the accuracy didn't increase, so this 2 more epochs was not necessary anymore. Now, what I want to do, I want to check the efficiency, scratchANN. I want to check the efficiency of this open source library I developed in C with the library, the TensorFlow we have on Python. So I load the data. Just one thing before I forget. I guess I mentioned that, but just to make sure you got the idea. Breast cancer, I downloaded those data using this Python code. I just loaded the data and then I saved data in a text file. I guess I said it, but just it's good to mention that again. Anyway, I load the data. Here I just wanted to know how many CPUs TensorFlow is going to use. 2 CPUs times every CPU 2 threads, so essentially 4 threads are going to be used in power computation. And then I standardize data. This is exactly the same as standardizing data with this function. Also the train split, it says 30% for tests, or here in my model we say 70% for the train, and the data are going to be automatically shuffled. This is the default input. This train test split has data already is going to be shuffled. And then we create the model, which is exactly the same as the model we created. ReLU for the first hidden layer and sigmoid for the last layer, and the model is a binary. And I just want to print out the metrics for accuracy. This is the model I just created, and if I want to summarize, get the summary in my model, I use this summary function here, which this summary works exactly the same way as this summary in the Python works also. Number of trainable parameter 2049, here also 2004. I exactly created the same concept, it's exactly the same multi-layer perceptor model. In scratchANN we have just SGD optimization algorithm is by default already set, and the learning rate we use 0.01, the same learning rate we have here. Then I train the model for 2 epochs, and you get this accuracy comparing with the accuracy we have in scratchANN. Let me run the code. I did run it just one time. I want to do it one more time. Just clean. Okay, so this is the accuracy after 2 epochs scratchANN get. This is the accuracy that the model using TensorFlow gets. I exactly implemented the batch size and the epochs, exactly everything is the same for training settings. I exactly implemented the same TensorFlow. The only reason, again, I covered in the previous video as well, the only difference, the only reason that scratchANN is working better, you can see after 2 epochs, this is like still 66%, but here I have 95%. Also on validation accuracy, I have 87%, which here is again is different. But anyway, if I run 2 more epochs, you can see after 4 epochs, this is good. Again, this is retraining the model. Technically, you have to recreate the model, reinitialize all the weights and biases, and then train this again. The concept of pressing this button one more time is the same as retraining for 2 more epochs. The model was already trained, and I just retrained it for 2 more epochs. Every time you have to recreate, reinitialize the weights and biases, and then train the model. You can see this time is 94%. So this tells me the reason scratchANN is working in cases like this better in the first try, like just first try, you get quite high accuracies. Maybe one time clean, and the only reason I see that this is working slightly better with one try on only 2 epochs is the now 85%. You can see every time the fluctuation is too high. The only difference, I believe, I don't know what's the implementation behind the TensorFlow MLP algorithm, MLP library that they have here, but the only difference I believe is for the initialization. To initialize the weights and biases, I'm using sodium library, which is, I guess, quite efficient more than many random function generators, random value generators. Anyway, other than that, everything is the same. But mind you, scratchANN maybe in initialization is a little bit better, but TensorFlow definitely is more robust model, because let's say scratchANN only has SGD optimization algorithm, but you have here multiple options. In the future, if you want to develop to have multiple different optimization algorithms, let's say Atom or global optimization, of course you can easily do that. You have access to all the codes for scratchANN here. Let's go try another setup. Let's remove this one, and now I want to change the activation function. So 33% of the first layer, this layer, 33% of neurons are going to have tangent hyperbolic activation function, 33% are going to have ReLU activation function, and 33% are going to have linear activation function. And then the last layer is still going to have sigma. The number of the configs in this layer is three different types I have here, so that's why I have to manually input this tree here to just given the size of the number of possible activation functions, not possible, the number of the different activation functions I have in the second layer. This is not quite user-friendly input. In the future, you can change it in a way that works for you. The last layer has only one config, and that's why this is 1. I don't want to change anything else. You can change, for example, this one if you want, but I just want to compare with the previous setup we have for the activation function to see how this is going to look. So clear, make again. And now this is the result I'm having. Maybe one more time. Wait, this. I guess this is the highest accuracy we can get. Necessarily, different activation function is not going to always help you. Sometimes there is a linear connection between inputs and outputs. Sometimes the model needs to capture a nonlinear connection between the inputs and outputs, first layer and last layer, the output layer. I guess this is pretty much everything. You can try different setups. Let's say you can, this model is quite small, just has one hidden layer. Maybe we can try it, I don't know, with, let's say, it's not necessary, but let's try 32 here and 16 here. So now I have 4 layers, which is 2 hidden layers. This means if you come here, change slightly the things that you have. Let's use this one, hyperbolic, and then call this one number 4, and this is the loud output. So now again, this I just added another hidden layer here. Okay, and this is not 64 anymore. This is 32, 16 neurons in the two hidden layers I have. So the first one has three activation functions, three different activation functions. The second one has one, the last one also has one. So we have to manually again add this one here. We want to run the program again, run the program, and I can see a little bit improve the thing, but the number of samples are not too high. I won't suggest going with too much large models if, although the number of trainable parameters actually here is less. Maybe let's just try 16 and 8. Actually, I'm decreasing the number of trainable parameters because the dataset is quite small. So now the number of trainable parameters is 600 something. The model is much more small. But first epoch it was not really good, but in second epoch I got quite efficient as much as the previous one. I would suggest actually to use this model rather than the other model we had. So maybe I can just add one more here for gradually decreasing the number of the, and then I wanna just add one more layer. I'm gonna call this one to version as well, and maybe I can do 50%. Again, this is the proportion of each activation function. So now I have 3, 2, 1, and the last one is also 1. Okay. Oh, and the only thing I need to do, this is going to be 3. This is actually going to be 6. This is going to be 5. And this is okay. So now I have in total 5 layers, and let's make it again. Well, actually it got even worse, so seems like maybe I can increase the number of epochs, maybe just go 10. Let's see if it does work. Well, after 10 epochs, seems like we got to the point that probably it was stuck in a local minimum, and then at one point it was able to pass this local minimum, and you can see the accuracy actually increase. This is if the problem, like, probably sometimes you see these kind of data, you're gonna say, okay, I need to change the optimization algorithm to maybe a global optimizer, but actually with just changing the architecture, the number of the hidden layers you have, you can solve this problem. Maybe I can just decrease even the learning rate. I think actually it's gonna make it worse. Just let's try it. Yeah, it got actually worse. Maybe I can actually increase the learning rate with this architecture, and yeah, it's actually got now better. So I guess if you increase, well, this was not necessary anymore. I would suggest after 4 epochs, I guess it's already, even 4 epochs is too much. I would suggest again after 2 epochs we would have stopped the training. I don't want to overfit the model I have. Yep, this is another test case study. You can go here and download the files on my GitHub. Probably I'm gonna make another video also for, in the next video I'm going to cover how to run the scratchANN to train your model on MNIST 784, the model should be quite larger because the number of samples is 60,000 and the number of the inputs are quite like a lot more than 30. Here we're going to have 700 something, and the number of the trainable parameter essentially is going to be much more, and that is going to be a lot more challenging for a multi-layer perceptron to be trained. So to check to ensure about the efficiency of the scratchANN, we need to do that, and we're going to compare again with the TensorFlow model we create on Python. Feel free to reach out also if you have any questions below here on the comments.